go back again. Okay, so welcome again. So as I said, the first faculty is Neeldhara Mishra, which she works in parameterized complexity and computation social choice. And this is me, Manoj Gupta, and I work in dynamic algorithms and fault tolerant algorithms. And Balgopal Komrat, and he works in computational complexity theory and circuit complexity. The next faculty is Diteshwar Das. He is the first faculty first faculty in computer science and engineering at IIT Gandhinagar, and he works in algorithms for algebraic and computational problems and computational complexity theory. And the last faculty in this group is Anirban Das Gupta, and he works in big data algorithms and algorithms for social networks. And he has also aligned interest in machine learning and others. And Nipun will be talking about the work he does in his presentation. So I will not be talking about what Anirban does. So I'll be only talking about the first 4 faculty, including me. Okay, so I have something in the chat. Okay. Okay, so what I'll do is I'll look at some problems that even we might ask you in your interviews. Okay, and I will just try to make connection with some of the works that we do in some of the work that our faculty do. And these are simple questions. As I said, we might even ask you these questions in your interview. And the first question is very easy. So what we have given you is some numbers, some n numbers, and we ask you to sort these numbers. And everyone knows how to sort numbers. Okay, so you take these numbers and you have sorted those numbers. And normally people, they just mug up that, okay, sorting takes n log n time. They have like many sorting algorithms. And we all know the sorting takes n log n time. There are many algorithms, merge sort, heap sort, or whatever. Okay, but there is something special about this input. Okay, if you see in this input, and if you look at 60, well, 60 is 2 away from its correct position in the final array. Okay. Similarly, if you look at 86, 86 is also 2 away from its correct position in the final array. 11 is actually 3 away from its correct position in the final array. Okay. In general, if you see here, all the numbers, okay, and this is, let's put it here, all the numbers in this given array are k away from their correct position in the final array, in the final sorted array. Okay, and where k is equal to 3. And given this special array, the question is that can you sort this special array in order nk time? So I don't want order n log n, I want nk where k is a parameter. Okay, so this is something extra that we are asking you. Okay, and normally you will find it pretty hard to think about because you have just learned your sorting algorithm. That is all. If we ask you anything extra, it requires some more work, and this is the kind of work that we expect you to do when you come here. Okay. Well, this is a simple problem, and what I'll ask you to do is actually try this problem. Okay. Now, how this relates with what Neeldhara does? Well, Neeldhara actually works on many theoretical problems which are actually NP hard or NP complete. Okay. And the solution to these problems are sometimes exponential, sometimes even maybe more than exponential. Okay, where n, so the running time for these problems is roughly 2 raised to n, where n is the input size. Okay, it can be even more than 2 raised to n. Now, the thing that she does is, well, can we design algorithms for these problems with a running time of, well, I want an exponential only in k, where k is a parameter. Okay, and in terms of n, I want polynomial of n. Okay, so n raised to 2, n raised to 3. Well, polynomial in n is fine, but the exponential should be only in terms of k. Okay, and these are called parameterized algorithm, and k is a parameter. So as we saw in our this example, well, there is an example. Oh, this is oops, what happened here? Oops. So this, okay, as we saw in this example, well, in this example, k was the parameter. Okay, okay, so let me again, okay. As we saw in this example, k was the parameter. Well, for Neeldhara's question, well, k might be some parameter of the input. Okay, For us, K was the parameter. Well, how far are the numbers from their correct position in the parameter? Okay. And these are called parameterized algorithms. Okay, so now I'll go to the second person, which is myself. And for me, well, I again look at a very, very simple problem. So suppose you are given an array which is already sorted. Okay. And what we can do is to the sorted arrays, we can add any number to this array. And after we have added this number, well, we may have to answer the following query. And what is the query? Well, report the number at an index k in the sorted array. For example, in the current array, well, at index 5, in the sorted array, you should report 18. Index 7, you should report 60. But now the hard part is that you have added an extra number. 1 second. So the hard part is that now we have added a number to this array. So let's assume that I have added a number 58. Okay. Now things become slightly complicated because, well, in the sorted array, now we should also sort 58. And in the sorted array that contains 58, you should tell me what is the number at index 2. And this is very easy to solve. Well, what I can do is I can find where should I place this number 58. Okay. And after I have placed this number 58 at its correct position, well, then everything is easy. Well, I can find what is the number at what index. So what I claim is that the update time of this algorithm, well, once 58 came, I put it at its correct position. Well, to put the number 58 at its correct position, I require order n time in the worst case, but the time taken to answer a query is just order 1. Okay, once I have this correct sorted array, to find what is the number at index k in the sorted array, it's very easy. It's just order 1. But, and again, I will ask you to try to do this on your own. Can you design an algorithm which has update and query time both order log n? Incidentally, this was the question which I first solved when I was myself a master's student, and my advisors told me that, okay, you want to do some research problem, first go and try to solve this question. This is not a hard question. This is something more than what you have learned in your bachelor's. Okay, so what are dynamic algorithms and how it relates to the previous problem, which I shared with you? Well, in dynamic algorithm, at each step, there is an update to the input. Okay, and your algorithm needs to update itself, and there might be a query. Well, what the query is, well, you have to report a property of the input, some property of the input. Well, in the previous example, the property was, well, what is the number at index k in the sorted array. Okay, and your algorithm would be judged by the update and query time. Okay, so this is in short dynamic algorithms. Let's go to the next faculty, which is Balgopal. And Balgopal works on many problems, but this is a problem that he shared with me, and I want to share it with you. And I'll also tell you what is the solution for this problem. And the problem is again related with numbers. Well, I have given you some numbers, and now I ask you, are there 3 numbers, I plus 1 and I plus 2 in these given numbers? Okay. So again, I've given you some numbers, and this is a very simple question. Are there 3 numbers, I plus 1, I plus 2 in this list? And the answer to this question is actually pretty easy. So I'll just say it on myself. Well, what I do is I will just sort these numbers. And once I have sorted these numbers, I will just try to find if I can find 3 numbers, which are I plus 1, I plus 2 in this sorted list. And in this case, it is indeed the case that you can find 3 numbers, 3 consecutive numbers after you have sorted. So this is a pretty simple problem, and the running time of this problem is order n log n. Okay. So now, how does it relate to what he has done? So he has some papers which solve the following problem. So what you can do is you can make a graph out of this particular problem. What I'll do is, let's assume that these are vertices in the graph, and you add an edge between 2 vertices if their absolute difference is less than or equal to 2. Okay. And if you do that, well, you can see that you can make a graph like this. Okay. And in this graph, again, I'm trying to solve the same problem. Well, can I find three numbers, I plus 1 and I plus 2? Well, but this is now a different problem. Well, if you see it in terms of graph, the problem is there a triangle in this graph? Okay. And this is one type of problem that Balgopal has been studying. Well, the problem is what is the hardness of such kind of problems? And can we look at some other graphs, like can we find the existence of cliques, or what is the hardness of the problem of finding cliques, or induced? Well, if you just I just don't want cliques. Well, on the vertices. Okay, so what should I say is that this is an induced problem. Okay, so I just don't want cliques. So Balgopal, can you say what was the term? It was induced. If you are there,
the induced subgraph, right?
Okay. So you want to okay. So you want to find if in this graph there is an induced graph which is a yeah. So this is what I forgot. Okay. So in this graph, can you find an induced graph which is a triangle? Well, in this case, actually it is the case. If you see 89, 90, and 91, well, this is an induced graph which is just a triangle. Well, one more thing that you can ask is whether there is a graph which is a triangle, okay, which is a subgraph. Whether you can find a subgraph in this graph which is a triangle. Well, even then this is true. Well, this is 11, 12, and 13. This is a subgraph which is a triangle. But harder problem is, can you find an induced graph which is a triangle? Okay. Well, in this case, well, there is an induced graph which is a triangle in this graph also. And this is the kind of problem that he has been trying to do, trying to solve. He has some papers on this. And one thing that he has been doing is, what is the hardness of these kind of problems? Okay, what if I look at graphs which are near cliques, not just cliques, which are near to cliques? Can you find those graphs quickly? Okay, so this is Balgopal, and the last faculty in this list that I will be talking about is Bireshwar. Okay, and Bireshwar's problem is slightly near to what Balgopal has been doing. So let's assume that you are given this graph G, and you have another graph which is H. Okay, and the problem is actually very, very same to what Balgopal's problem is. So now I don't want induced graph. I just want to check if I can find this graph H in G. So is there a subgraph in G which is similar to H? And this is called the subgraph isomorphism problem. So does H exist in G? Well, in this case, if you see, well, this is indeed the case. So there is a subgraph in G which is similar to H. Okay. So unfortunately, this problem is NP complete. So what Bireshwar does is, well, he works on a very special case of this problem. And in this special case, well, G and H has same number of vertices. So in this case, you can see that G has 8 vertices and H also has 8 vertices. And the question remains same. Well, in this case, the question is, are these two graphs same? Okay. And it seems that, well, if you see from naked eye, you will feel that these two graphs are not same, but these two graphs are actually same. And if you see now, I have colored, so this node is actually this node here. So there is a corresponding between colors. So this node is this node. And I claim that these two graphs are same. So this blue colored vertex is adjacent to this maroon color. Well, I say this is red and this is yellow. And even in this case, this blue color is adjacent to maroon, red, and yellow. And let's make it slightly easier for everyone. I'll make the second graph also by changing. And now you can see both the graphs are actually same. Okay, so this is called the graph isomorphism problem. So let me define the problem that he has been working on, or the variant of the problem that he has been working on. So let G and H be two graphs on n vertices. And the question is, are these two graphs same? Or formally, is there a bisection from vertices of G to vertices of H, so a function from V of G to V of H, such that if U and V are adjacent in G, then FU and FV are adjacent in H. Okay. And this is called the graph isomorphism problem, and he has been working on this, on a variant of this problem. Okay, so I think I have covered all the faculty members, and I think this is all that I have. And thank you.